Assalamualaikum warahmatullahi ta'ala wabarakatuh. Today, I'm going to share with you another example on simply supported beam, which is simply supported flange beam doubly reinforced. Previously, we have go through on simply supported flange beam singly reinforced. Okay, so this is the beam that we are going to design, which is a 7 meter length, and then there is a action that is acting on top of this beam, which is a brick wall, finishes, shielding and services variable action. So here is the section of the beam dimension where the effective weight of flange BEFF is equal to 600 millimeter. So I do already calculate the BEFF earlier. So basically you have to, this value is not come from the assumption. You have to determine each of the value BW, H, and also BEFS based on the preliminary sizing for the BW and also H. For the BEFF, you have to calculate the effective width of flange. So you may refer to my another video in my YouTube channel. So in this case, okay, the nominal cover given here is 35 millimeter, as I said usually. So the nominal cover should be calculated based on three conditions. Okay, the first one is due to the fire resistance, second one due to the exposure class, and then the third one due to the bond requirement. So here are the given data that I'm going to use in order for me to design the beam. Okay, there is an additional permanent action here, 20 kilonewton per meter. So on top of this beam, so you have not to forget about this. Maybe this load is due to some external structure or that is applied to this beam. Okay, so the first step, you have to calculate the design action. As usual, you have to calculate the permanent action and also variable action. So the self-weight of the beam is 25 times 0.175 times 0.45 is equal to 1.969 kilonewton per meter. Then the brick wall is 2.6. For this time, I'm using 2.6 times 3, okay, equal to 7.8. Okay, and then the finishes, shielding and services, additional permanent action. Therefore, the total permanent action is 30.319 kilonewton per meter. And then the total variable action here is 3 kilonewton per meter. Then we get the design action here, 45.43 kilonewton per meter. As usual, after we get all this action, so we have to calculate and analyze the beam to determine the shear force and also bending moment. So I'm using the same method because this is the simply supported beam. So the length of the beam is 7 meters. So for the maximum shear force is equal to WL over 2, which is 159.01 kilonewton. And then the maximum moment is WL squared over 8 for simply supported beam, which is 278.26 kilonewton meter. So you may also, using the area of this shear force, you will get the maximum moment here. Okay. Next, we have to calculate the design reinforcement. So the first one, we have to calculate the effective depth. So D is equal to H minus C nominal minus diameter link minus diameter bar over 2. So in my case here, my H is 400, therefore my effective depth is 351 millimeter. So next process in flange beam, you have to calculate the moment of flange. So what is the moment of flange? So here is the formula. You may refer to the design appendix given. Okay, so the moment of flange is equal to 0.567 FCK BF, which is BEFF, HFD minus HF over 2. Then the answer is 251.75 kilonewton meter. So we have to compare this MF, okay, moment of flange with the maximum moment M. So M more than MF is therefore neutral axis lies below flange, designed as a flange section. So if the M is less than MF, neutral axis lies in flange, designed as a rectangular section. So you don't confuse on that conclusion. So next, if you would like to design as a flange section, so next you have to calculate the ultimate moment of flange by using beta FFCK BFD squared by using this formula. Then you get the MUF equal to 271.35 kilonewton meter. So the purpose of calculate the ultimate moment of flange for the beam is to determine either the beam that we are going to design is a singly or doubly reinforced. Compared to the rectangular beam, what we have to do, we have to calculate K in order for us to determine either the beam that we're going to design is singly or doubly reinforced, either K less than K balun or K more than K balun. But for flange beam, we have to compare the maximum moment and maximum with the ultimate moment of flange, either it is more or less. Okay, in my case here, the conclusion is the maximum moment is more than ultimate moment of flange, which is the compression reinforcement is required, therefore the beam is doubly reinforced. And then we have to design the compression reinforcement first. So in order for us to calculate the compression reinforcement, which is at the top reinforcement of the beam, so this is the equation. So AS prime is equal to M minus MUF over 0.87 FYK D minus D prime. So I got the answer 63.04 millimeter squared. Provide 2H12226 millimeter squared by referring the dimension table. Normally, if we have a doubly reinforced, it is a normal condition of the reinforcement. It is illogic if you get your AS prime here is bigger than your AS. Normally, your AS prime, the compression reinforcement, much more smaller than tension reinforcement. So you have to bear in your mind so that you know that your answer is correct or wrong. And then we have to calculate the tension reinforcement here. So the tension reinforcement by using this formula, AS equal to 0.167 FCK BWD plus 0.567 FCK HF BF minus BW over 0.87 FYK plus AS prime. So this AS prime is using this AS prime required here, which is 63.04. Then I got the answer 2036. Then I provide 5-25 to 450 millimeters square. As usual, we have to calculate the AS minimum and also AS maximum for us to compare with our AS provided here. Okay, so we have to make sure that AS provided here should be in between AS minimum and also AS maximum. So have to be careful here. So the B that you have to use here in AS minimum and AS maximum, not BEFF. It's actually your BW175 millimeter. So please be careful on that because some of my students using a wrong value in incorrect value in their calculation. They use BEFF, which is 600. So it is totally wrong. So the B here is BW. So I made a conclusion here. My AS minimum is less than AS provided and less than AS maximum. Next, after we define the AS minimum is in between AS provided and AS maximum, the design for the main reinforcement is okay. We proceed on the next step, which is a design shear reinforcement. So as usual, shear reinforcement. So we have to compare our VED with VRDC or Vmin. The first one, we have to compare the VRDC and also Vmin here. So in my case here, so my VRDC is bigger than Vmin. Therefore, I'm compared with VED. Therefore, shear reinforcement is not required. Therefore, provide the minimum shear link. So you have to make sure all those value that you are using here is correct. So especially for K value. So you have to make sure the K value is less than 2 mm and then the rho value here is less than 0.02. So if you get more than this value, you have to use this value. Okay, so here is the conclusion. The shear reinforcement is not required, therefore provide the minimum shearing by using this formula. SW over S equal to 0.08 BW square root FCK over FYK. Then I got the answer 0.14. Provide HH300 center to center 0.335 0.035. Okay, so what is actually shear reinforcement? So the shear reinforcement is the element that we are going to use in order for us to tie up the main reinforcement. Other than that, it is to cater the shear failure of the structure. So what you have to understand, okay, about this shear reinforcement is, okay, why the shear reinforcement is not required when the maximum shear force is more than the maximum resistance shear. So this is because the maximum capacity of the shear force for the beam is actually satisfied to fulfill the requirement of the beam size. Okay, so that's why without shear reinforcement, this beam is able to sustain the action that we apply to the structure. Okay, but it is not enough in terms of the structural detailing if we do not have this shear reinforcement. So we need this shear reinforcement in order to strengthen more the shear behavior of the beam in order to complement the main reinforcement for the beam. So which is for the maximum moment. Okay, so you have to understand this situation, why we still need the shear reinforcement if it is not required. So this is not kinds of thing we call as a over design. It's not an over design condition. It's actually the required condition that we have to provide the shearing for the reinforcement, but we provide the minimum shearing here. Okay, not the more than that. Okay, so next process is the deflection. So as usual, the deflection process, we have to calculate three, which is L over the basic, L over the allowable, and L over the actual. So the first one, we have to calculate rho and also rho prime. So in my case here, I do have a value for the rho prime here. So because this is a doubly reinforced, and I have the AS prime value. That's why we have the rho prime value here. So uh, we compare the rho naught with a rho. Okay, so in my case here, the rho naught is less than rho, therefore we use equation 7.16b, okay, for L over D basics. Okay, so I got the answer here is 12.24 for the L over D basics, and then the L over D allowable is equal to L over D basic times modification factor of the reinforcement. So L over D basic is 12.24. Modification factor of the reinforcement is AS provided over AS required. Okay, tension reinforcement. So not compression reinforcement times the modification factor of the span. Because of this span is a 7 meter, so that's why I'm using 1. So if it's more than 7 meter, so you have to calculate the ratio 7 over L effective of the beam. And then the L over the effect allowable is 14.72. So L over the allowable here, okay, so is L over D, which is 7,000 over D is 351, 19.84. Therefore, the conclusion here, L over the actual that I found here is more than L over D allowable. Therefore, the deflection check failed. This is supposed to be not the condition that we are going to go through, or the result that we get when we designing a beam. So we have to make sure each of the parameter that we calculate and the ultimate limit state and also serviceability limit state is passed. So in my case here, okay, what we have to do in order for us to make sure that the deflection check fail. So we have to check which parameter that is contribute to the deflection. So in my case here, we know that one of the parameter that is reflected to deflection is our D. So if we can increase our D here, so we may reduce the L over the actual. So for example, if the D is become 400, so absolutely the actual L over the ratio here will be lesser. So that's why we can increase the beam depth H. Okay, or if this situation, okay, we cannot get the answer is still pass, there is another solution. What we can do is we may reduce the beam span L by adding column in between the beam. So you may refer to my another lecture on the common failure of the beam in my YouTube channel. So what we have to do, we have to redesign the beam after changing the beam configuration and dimension from the beginning, because it will reflect the self-weight of the beam, and then it will reflect the bending moment and also shear force. So this is a normal process that we have to do. That's why I do already told you that the early assumption or early determination of the plan configuration for the structure layout plan is really important for you to make sure that, for example, to make sure that your design will not fail, because we have to do redesign of the structure if your structure or your parameter that you determine is fail. So this is the process sometimes make us give up. So please don't please take into consideration what I do already telling to you guys and sharing to you guys on the common failure of the beam, so that you have to be careful when you start on designing and determine a specification for reinforced concrete beam design. So next process, we have to check the crack check. Okay, so this is the detailing of the reinforcement that I'm going to have for my beam, which is 5H25. I arrange 2 to 1. Okay, so I have two spacing here. So as usual, the first one we have to calculate the steel stress. So the steel stress here is 299, and then the WK is 0.3 millimeter. This depends on the exposure class that you use in your design. So by interpolation, I got the allowable spacing is 126.25. Then the actual spacing is equal to B minus 2. C nominal minus 2 diameter bar is supposed to be 3 diameter bar here. Here is correct, here is wrong, sorry. Okay, and divided by 2 spacing, I got 19.5. So S minimum is 25 millimeter, is more than S actual 19.5 millimeter, and less than S allowable 126.25 millimeter. So the deflection check is failed, same as what we get in the deflection check. Okay, so oh sorry, this is a crack check fail. So sorry, it is typo. So cracking check can consider pass by using the maximum size of cost aggregate is 10 mm. If, for example, if you assume the maximum size of the aggregate is 25 mm, because S minimum is refer to the aggregate. So if the aggregate can pass through this reinforcement, okay, so it will easily for the concrete to be compacted. So there will no honeycomb problem happen here. So if you're using a S minimum or the aggregate size is 10 mm, then your deflection, your crack check can consider pass. So you have to make sure you have to tell, if you order the ready mix concrete, you have to tell the ready mix concrete the maximum aggregate size that we are going to use for this structure is 10 mm. So if you would like to use a 10 mm, if you would like to use a 20 mm or 25 mm, it's okay. So but you have to make sure that the spacing here is passed, so that the crack check will be passed. Okay, what we have to do, the same things again that we have to do, the solution in order for us to make sure that the cracking check is passed is reduce the diameter of the bar of the or numbers of bar. So we can rearrange this bar, okay, become only one spacing. So for example, we can have for H30, okay. So then you have to make sure that by increasing the diameter bar and reducing the numbers of bar, it should be fulfill the requirement of AS minimum and also AS maximum. It should in between that value, and then increase the dimension of beam width BW here in order to increase the spacing of the bar. If you would like to maintain or remain the numbers of bar like this. Okay, so this is the things that we can do in order for us to solve the problem when we are facing a failure of the design based on this calculation. Okay, here is the detailing of the reinforcement for the beam, which is the longitudinal section and also cross section. So I hope that by this demonstration, it will give a very good view to all of you guys how to design the simply supported flange beam. So I hope that you can identify the difference between singly reinforced and doubly reinforced rectangular beam and also flange beam. I hope if you have any question, you may comment or you may WhatsApp me or you may email me. So that's it, my sharing session for today. Thank you. Assalamualaikum.